Today I'm going to explain why AC circuits have a phase angle. If you've worked with alternating current, you're familiar with phase angle and you've probably calculated it, but why does the circuit have a phase angle in the first place? Well, first of all, let's explain what we mean by phase angle. In alternating current, we have a voltage that is constantly changing. Usually it follows a sine wave, so I'm going to draw my best sine wave here. So the voltage goes up to some certain voltage, goes back down. Typically, in alternating current, it will cross 0 volts, so I'll put a 0 volt line right there. The voltage goes down to some negative voltage and then back up to 0, and then it repeats that over and over again. In North America, this happens in 16.6 milliseconds, so this is our time axis over here, and our voltage axis is the vertical axis. And in most of the world, this happens in 20 milliseconds because most of the world uses a 50 hertz standard, where in North America we use a 60 hertz standard, so it's a little faster in North America. But there is our voltage constantly changing. The voltage goes up, voltage goes down, voltage goes back up over time, and this takes 16.6 or 20 milliseconds depending on where you are, but as far as the phase angle is concerned, that doesn't matter. Now remember that we can measure a sine wave as a number of degrees. As a matter of fact, a sine wave is closely related to a circle, so we actually measure the time it takes to reach one complete cycle, not really the time, but just the parts of the wave in degrees, just like a circle, and one cycle is 360 degrees. So what do we mean by a phase angle? What we're concerned about is the current through the circuit. So let's take a look at a DC circuit for just a moment. I'm just going to draw a battery here. And we'll just put a resistor in there, very simple circuit. We'll make this 10 volts and make this 10 ohms. So what are we concerned about? We're concerned about the current through this circuit. 10 ohms, divide that into 10 volts. We know that there is 1 amp of current flowing in the circuit. Okay, in an AC circuit, we have the same thing. I'm going to draw a simple AC circuit with a capacitor. There's our alternating current source. We'll see this bigger a little bit later, but right now we'll just draw it here. There's our resistor, there's our capacitor, and let's say this is 50 volts at 60 hertz, and we'll make this 30 ohms and 100 microfarad. It's not going to do much calculation right now, but we'll use those numbers in a moment. So we want to know what the current is through this circuit. I'm not going to go through all the calculations just now, but one thing we do know, we're going to have a certain amount of current, and I happen to know it's going to be 1.25 amps. But we also know that the current is not going to be peaking at the same time as the voltage. In other words, when the voltage reaches its highest point, the current's going to reach its highest point at some other time. And because this is a capacitor, that means the current's going to reach its highest point sometime before the voltage does. If this was an inductor, it would happen sometime after the voltage. But we're not concerned about that. We're just going to look at capacitance in this particular circuit. Remember that an inductor would be later rather than earlier. So let's take a look at about where the current would be here. So we know the current's going to peak earlier. So here comes the current. It's going to peak earlier, and it's going to follow a path something like that. And so here's the moment that the voltage peaks and the current peaks some earlier time. And we measure that in a certain number of degrees. And that's what we're interested in, is how many degrees before the voltage does the current peak. And that's called the phase angle, which I've represented with the Greek letter theta there. The crummy little theta. Let's draw that again. There we go. There's a nice little Greek letter theta. So the current peaks sometime before the voltage does. And the current hits 0 sometime before the voltage does, and we measure that difference in degrees, and it's called the phase angle. So everywhere along these curves, everything happens with the current some number of degrees before it happens with the voltage. And that's what the phase angle of the circuit is. It's the lead or lag angle of the current compared to the voltage. So why does this happen? Well, to explain it, let's first look at how a capacitor acts when it charges and discharges with direct current. So I'm going to draw a battery here and a resistor and put our capacitor here. And we're going to put a little switch here to help us do with what we need to with the circuit and put another switch here. This switch is here just to make sure that capacitor is discharged when we start everything off. Let's make this 1 volt, 1 ohm, and 1 farad. I use those numbers in this demonstration because not only are they easy to deal with, but they show something important about capacitors. But if you want to know more about this particular circuit, you can watch my video and read the textbook material that I have linked in the video below. We're just going to go through it real quickly right now. So what I'm going to do is close this switch, make sure that capacitor is completely discharged. Now I'm going to open the switch and I'm going to close this one. So what's going to happen at that moment? We're going to have current surge into this capacitor, and it's going to spread out on this top plate. And as that piles on there, it's going to drive current out the bottom. Now, of course, we know it's electrons going the opposite direction, and electrons on this plate are repelling them off the other plate. But in this class, as in most of the electronics industry and academia, we use conventional current because it's easier to analyze circuits with current going from a high voltage to a low voltage rather than the other way around. Okay, so current goes in, current comes out. We see the current going in, we see it coming out. Looks like it's going right through. It's not the same current coming out that went in, but we can't tell the difference. So what does that capacitor look like? It looks like a short circuit at that moment in time. And if we put a voltmeter across here, what are we going to see? Well, first of all, a short circuit, no matter how much current's going through it, there's no resistance to cause a backup of pressure where the current goes in, and so there's not going to be any difference in voltage from one side to the other. And what does the voltmeter tell us? It tells us the difference in voltage. One voltage is meaningless without another voltage to compare it to, and that's what a voltmeter tells us. It tells us the difference in voltage between the red lead and the black lead. So at this point here, there is no difference. So it says 0 volts. And how about the current? Well, right now, the capacitor is basically invisible to the circuit, so all we have left is the battery and the resistor. So it's a 1 volt battery, a 1 ohm resistor, divide the 1 ohm into the 1 volt, we get 1 amp of current. So at the moment we throw the switch, we have 0 volts across the capacitor and our maximum current through the circuit. The maximum current, or the current at any time, is determined by the amount of voltage that we have across this resistor. Right now that's just 1 volt, 1 ohm, 1 amp. Okay, but as time goes by, that capacitor is going to charge. And it's like putting air into an air tank or maybe a tire. You put a little air in, you get some pressure. You put more air in, you get more pressure. And as you put more and more air in, you get more and more pressure until one of two things happens. Either you can't put any more because your tire's pushing back as hard as your pump is, or the tire explodes or the air tank explodes. A capacitor works exactly the same way, except of course voltage is pressure. We put a little electricity in, we get a little voltage. We put more in, we get more voltage, and the more we put in, the more voltage we get, until one of two things happens. Either we can't push anymore, either this has the same voltage as our battery and it's pushing back just as hard as the battery is, so there's no current, or the insulation fails and maybe even the capacitor could explode. So eventually what's going to happen is this capacitor is going to charge up until, put our voltmeter across here again, it's going to have 1 volt. And at that point, the capacitor voltage is the same as our source voltage, and because this voltage is the same as that, this is pushing with 1 volt, that's pushing the other way with 1 volt. How much current is flowing? None. They're pushing in opposite directions. So there's no current flowing through the resistor or the rest of the circuit, so we have 0 amps. So let's go ahead and draw the graph of what just happened. Here is time, and we'll do this in seconds. The reason I chose 1 ohm and 1 farad is because 1 second is the time it takes to charge to 63.2% of the source voltage. And then after 5 seconds, or 5 time constants, so 1 time constant, 63.2%, 5 time constants, near as makes no difference, 100%. So remember what happened when we closed that switch. Here's our voltage, here's our current. Remember, our voltage was 0 because the capacitor looked like a short circuit. So 0 volts, maximum current. What was it? We had 1 volt, 1 ohm. We had, let's just draw it like 1 amp. So 0 volts and 1 amp. That's going to charge up on a curve that looks something like that. And the current, as that capacitor charges, it pushes back more and more, and so we get less and less current, and then we eventually, after the same amount of time, we have no current. So after about 5 seconds, in the case of that circuit we just had, our capacitor has charged up to 1 volt, or our source voltage, and our current is now at 0 amps. So a couple of important points there. When we first flip the switch, the capacitor looks like a short circuit. Let's go ahead and remember this graph. This is when we flip the switch. This is about 5 seconds later with that particular circuit. We flip the switch, we have our maximum current and 0 volts. After about 5 time constants, 5 seconds in this case, we have our maximum voltage and 0 current. So let's take another quick look at what's going on there with our circuit. I'll forego the switches at this time. At the time we threw the switch, we had 1 volt here and 0 volts here. So we had 1 volt across the capacitor, so we had 1 amp of current. Once again, 1 volt on this side, 0 volts on that side. So we have 1 amp of current. After 5 seconds, this is up to 1 volt. So now we have 1 volt on this side and 1 volt on this side. So we have the same voltage on both sides. How much voltage is that? Remember, if the voltage is the same on both sides, that by definition is 0 volts. It's the difference in voltage. 0 volts is not the absence of voltage. 0 volts simply means that 2 voltages are the same. Typically it means that the red probe of our voltmeter is at the same voltage as our black lead, but what it means is that 2 voltages are the same. There is 0 difference. So 0 volts. So at first, 1 volt and 0 volts, a total of 1 volt across the capacitor. After a while, we have 1 volt here, 1 volt there, and 0 volts across it. Remember this because this is part of what causes the phase angle, is these changes in voltage across the resistor. So now what we're going to do is take a look at an AC circuit and analyze it at different points in time and see how it acts like a DC circuit. But the difference is this voltage is constantly changing. Instead of it being steady, the capacitor charges and stays there. This voltage is constantly changing. Let's take a quick look at what would happen if this did change. So this charged up to 1 volt. What if this kept on going? What if by the time this got to 1 volt, this was 2 volts? Well, now this is pushing this way harder than that, so it's not going to stop charging. It's going to continue to charge. So if this voltage goes up, that's going to continue to charge. What happens if this goes down now, back to 1 volt? Well, now, what do we have? We have something like maybe 2 volts here and 1 volt there. Now we have more voltage on this side than that side, and it's going to push the opposite direction. So this voltage goes up. As long as this voltage is higher than that voltage, the capacitor will charge. But as soon as this voltage drops below the capacitor's voltage, it'll start discharging. So that's basically what the AC circuit does. It's like a DC voltage, but the voltage is constantly changing. And if it changes in a periodic way, we call it alternating current. So let's take a look at how that circuit works at different moments in time and analyze why we get a phase angle. So here's the circuit I'm going to use. There's our alternating current source. I'll use 50 volts at 60 hertz, although the frequency doesn't really matter too much at this point. It matters for calculating different parameters of the circuit, but for the phase angle, what we need to know for the phase angle, it's somewhat inconsequential. So now I'm going to put a resistor here and a capacitor. Now I'm going to make this 30 ohms and 100 microfarads. So what's going to happen with this circuit? Well, of course this voltage is going to go up, and this capacitor is going to start charging, and it's going to try to charge toward, well, whatever voltage this is. Remember what's happening, that voltage is going up and down and up and down, and it says 50 volts, but that's the RMS voltage. It actually peaks at about 70 volts. So that keeps going up, and as that's going up and up, this is charging, and then eventually that's going to drop. As long as this has not caught up, it will continue to charge. And if this starts to fall, As long as this is still higher, it'll still continue to charge, but as soon as this voltage falls below the voltage here, it'll start to discharge. Now let's take a look at a graph of that and see what the consequences are. So here I have a graph of a sine wave, and it shows 360 degrees, or one cycle of the sine wave, and each one of the vertical lines is 10 degrees. The horizontal lines represent voltage. Each horizontal line is 20 volts. So we have this 50 volt sine wave, which actually peaks at about 70 volts and then goes to zero, then peaks at again at a minus 70 volts, making our complete cycle. And once again, it's 360 degrees across. Now, let's look at what happens as that capacitor charges. Let's pick it up right here where the voltage crosses zero on its way up. Now, the source voltage is higher than the capacitor voltage, so the capacitor is going to charge and is going to keep charging. But the capacitor voltage can't catch up to the source voltage because the source voltage keeps going up. And look, it even kind of charges in a straight line here instead of heeling over. But right here, the source voltage peaks and starts to drop. But as long as it is higher than the capacitor voltage, the capacitor continues to charge, but it's not charging as fast because the voltage is coming down, so the capacitor voltage starts to heel over. And then right here, the source voltage has come down and now meets the capacitor voltage. Now what must happen at this point? Well, once the source voltage goes below the capacitor must start discharging. So here we see the capacitor voltage peaking sometime after the source voltage peak because it's lagging behind in its charging. But as soon as the source voltage crosses the capacitor starts to discharge. So the capacitor voltage must peak where it crosses the source voltage because that's where they become equal. And if we look at the graph, we see this is happening when the battery voltage, remember the battery voltage is going up and down, it's really a AC source here. And so when this reaches at about 44 volts, it's dropping down, this is going up, but they meet when this reaches 44 volts. So at the point that the capacitor voltage and the source voltage meet, how much voltage is across the resistor? We have 44 volts on this side, 44 volts on that side. In this case, they're positive, but if it was negative, it would be the same thing. How much voltage is across the resistor? 0 volts. So with 0 volts across the resistor, how much current is flowing? 0 amps. So two things are happening at this point in the graph. We see that the capacitor voltage must peak where it crosses the source voltage. Now this is going to happen at a different time depending on your combination of resistor and capacitor. If you have more resistance or more capacitance, it's going to take longer for the capacitor to charge, so this is going to happen later. If you have less resistance or less capacitance, the capacitor is going to charge faster, and so it's going to happen sooner. But the voltage will peak where it crosses the source voltage. It has to, because when the source voltage is higher, it's charging. When the source voltage is lower, it's discharging. And so that's the point where that changes. So your capacitor voltage will always peak when it crosses the source voltage. This is the primary factor that determines the phase angle, but it's not the phase angle. This is the phase lag of the capacitor voltage. And again, we see that at that point, there's going to be 0 volts across the resistor. So how much current do we have in the circuit? 0. So at the point that these two voltages are equal, we have 0 amps of current. And that was just like the DC circuit. When the capacitor reached the source voltage, there was 0 current flowing through the resistor, and so we had 0 current through the circuit, and we had our maximum voltage across the capacitor. So just like the DC circuit, in fact, we're looking at this as a DC circuit. Now we need to look at the next factor that leads to the phase angle between the current and the voltage source in the circuit. So we've already seen that the current must be 0 when the capacitor voltage crosses the source voltage. Now we know that the voltage across the capacitor is going to be 90 degrees out of phase with the current. So why is that? Well, it has to be. First of all, we look here and we see that just like in the DC circuit, when the capacitor voltage is at its maximum, the current must be 0. Now let's look at when the capacitor voltage is 0. So if we take a look at the circuit here, this voltage is going to reach 0 at some point. And the source voltage at that point is going to be about minus 50 volts. So what do we have here? We have 0 volts on that side of the resistor and approximately minus 50 volts there. So we have a 50 volt difference. That's going to give us a current going in the opposite direction now, because the capacitor is now discharging, of 1.66 amps flowing in the opposite direction. And that's going to be our peak current. That's going to be the highest current we get, because after we pass that point, well, this is no longer 0. That's going to be going lower, and it's just the point where we get the greatest difference in voltage across that capacitor. So what have we seen so far? When the capacitor voltage peaks, it's going to be at the point it's at the same voltage as the source voltage, so the voltage is equal on both sides of the resistor, 0 current. When the capacitor voltage reaches 0, it's going to be at the point where we have the greatest difference in voltage across the resistor, and there's where we get our peak current. So let me give that a quick drawing. Here is our capacitor voltage. Let me draw a 0 line here. And our current is going to be happening sometime before that, but we do know that when the capacitor voltage reaches its peak, that the current through the circuit will be 0, because at that point is when it's crossing the source voltage. So they're equal, so we get 0 amps of current. But then when this reaches 0, we just determine that's when we're going to get our greatest current. So when the capacitor voltage peaks, we get 0 amps of current. When the capacitor voltage reaches 0, we get our maximum current. And then when that current comes over here and reaches 0, we already determined that when the current is 0, we have our maximum voltage across the capacitor. And then when that voltage reaches 0, what are we going to get? We're going to get our maximum current, and this just keeps happening over and over again. 0, maximum, maximum, 0. And so look where they are. Each time that happens is 90 degrees. So that's why we have that 90-degree phase difference in the voltage and current at the capacitor, because of this. Capacitor voltage is maximum, current through the circuit must be 0. Capacitor voltage is 0, the current through the circuit must be maximum, and therefore that's happening 90 degrees apart. So we're almost there. We almost know why we have the phase angle. So we have the source voltage, and then the capacitor voltage, and these happen some angle, which we haven't determined yet, and that changes depending on the resistor and capacitor combination. So less resistance or less capacitance happens sooner, more resistance or more capacitance, it happens later. So that's what determines this, and this ultimately determines the phase angle. But if I redraw this, we once again have our source voltage and then our capacitor voltage, but now we know that the current through the circuit is going to be 90 degrees before that capacitor voltage, and that is the final step that determines what the actual phase angle is. So here's our source voltage, here's our capacitor voltage, and our current is going to be somewhere ahead of that. So if we look at our graph here, we have the source voltage peaking here. The capacitor voltage peaks sometime later, and that happens to be in this particular case, we have the capacitor voltage peaking 49 degrees after the source voltage, but then the circuit current is going to be 90 degrees before that. So we take the lag of our capacitor voltage behind the source voltage, subtract 90 degrees from that, and we get the phase angle of our current. Notice that the current peaks when the capacitor voltage is 0, and the current is 0 when the capacitor voltage peaks. They're 90 degrees out of phase, just as they should be, and that is why we get a phase angle in our circuit. Ultimately, it's caused by the capacitor lagging behind the source voltage, but the actual angle of the current through the circuit has to do with the fact that it's 90 degrees ahead of the capacitor voltage. So the capacitor voltage ultimately determines what the phase angle is, but it's going to be the capacitor voltage minus 90 degrees, and that's our final phase angle. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.